All right. I think we should slowly start. So welcome everyone to our online seminar. Today it's our great pleasure to have Sourabh Paul from the University of the Western Cape in South Africa. And he's going to talk about H1 intensity mapping with the MIGHTEE survey, power spectrum estimates. So please go ahead.
Okay, thanks for the introduction and having me here. I'm a postdoc at the University of the Western Cape, and today I'm going to talk about the work that we have been doing on the H1 intensity mapping with Meerkat in the interferometric mode. Like some of you know, the intensity mapping experiment are done on the single dish mode. But today I'm going to talk about that what we can do or what we can achieve in the interferometer mode, and in terms of like how we can detect the H1 in the statistical way. So this work is done with collaboration with Mario Santos, Junaid, and the MIGHTEE collaboration. So just to give a brief outline of the talk. So first I'm going to briefly give introduction to the intensity mapping, what it is and what is the goal of an intensity mapping. And then I'm going to talk about the interferometric intensity mapping with Meerkat, and then the statistical detection of H1 with the MIGHTEE survey, that how we use the MIGHTEE data for our interferometric intensity mapping experiment. And the next, I'll talk about the simulation pipeline that we have developed recently. So the goal of this pipeline is to emulate MIGHTEE observation from the Meerkat and how we can go from data to the pulse spectrum domain. And then the constraint that we can get on the H1 on semilinear scales at redshift 0.27. And the final plot would be the sensitivity estimates that we obtain from the MIGHTEE survey. And then I'll conclude. So the recent any cosmological probe tried to understand this large scale structure. The idea is that the matter distributed is in the cosmic wave form, and we want to know we want to get as more information as possible from the many surveys as possible so that we can understand the matter distribution in the universe. So this image that you may have seen many times, it's from the Millennium simulation. It shows the matter distribution in terms of in the form of cosmic wave. And just to give you an idea of the scale here, like each bright dots are a cluster of galaxies. They are not individual galaxies. So each cluster of galaxies contains of 100 to 1,000 galaxies. And the one at the center is like a supercluster that contains some 10,000 galaxies and more. So we are really talking about like very large scales here. And the reason that we want to probe this large scale structure, because we can get information about many quantities like age geometry and expansion rate of the universe, and also the content and the nature of the dark matter, dark energy, neutrino physics, and like the initial condition of the universe. That's why study of the large scale structure is really very important. And then one of the key science goal for like any large scale cosmological survey or say intensity mapping is to probe the baryonic acoustic oscillation. So these are the relic acoustic peaks that are produced like before recombination, and they are present in the CMB, and they are observed in the distribution of the galaxies. So what they are actually is like there is an excess probability to find galaxy pairs separated by large distance, which is about 150 megaparsec co-moving distance. And the reason we want to probe these scales because they are key to constrain the angular diameter distance and the Hubble function. And there are many experiments that are going on which try to probe these BAO scales. And it's like there are like special purpose-built experiments, something like Bingo, Chime, Hyrax, Tianlai, which try to probe these scales. So among these, like Chime, Hyrax, and Tianlai, they are in the interferometric mode, like they're specially designed interferometers to their main science goal is to detect the BAO structures. And so this is a like 3D map of the universe that I guess you have seen, many of you have seen, like it came a few days back. What it shows is the Hubble volume, and the one in the colors are shown is the galaxies, quasars, and many other objects that we have got detection so far. And the idea is to like map out the entire volume as much as possible. So the main goal of any cosmological experiments is to fill up this Hubble volume, so that we can see the more structures, so that we can get more information out of this. And that's in this context, the intensity mapping is important. Like so, this is an alternate way to probe the large scale structure. One way is to like find individual galaxies and to study the matter distribution. But also, like each galaxy hosts a given H1 mass. Like after ionization, all the neutral hydrogen are within damped Lyman alpha systems within galaxies, which are kind of shielded from the ionizing radiation, so that they can stay in the neutral state. And we can sort of detect the 21 centimeter emission from those neutral hydrogen. So the idea is here to not detect H1 from individual galaxies. That is really difficult because of the sensitivity. We can only detect H1 from galaxies in the only nearby universe, like below 0.1 or so. So to get to the high redshift universe, what the idea is here to make low angular resolution maps of the universe. So we don't worry about much about the resolution here. So if our pixels in the map are really high, we can collectively detect like more H1 emission from that pixel. So from a galaxy distribution like this, we can have an intensity H1 intensity map, something like this on the right side. So the idea is here to from this map, we want to study the underlying matter distribution, because the H1 follows the dark matter distribution with some bias. So if we can detect the intensity map, we can effectively probe the underlying matter distribution, and that's the goal of the intensity mapping experiments. And the one way it is more promising than galaxy surveys, because in cases where number counts are very steep for those galaxies, or the survey depth is very shallow. And and one advantage with such line intensity mapping cases is that there is a one-to-one correspondence between the observed frequency and redshift. So we can actually get a very high redshift resolution from the frequency information, because the rest frame wavelength of the neutral, that 21 centimeter emission is 21 centimeter. But as we go to higher redshift, we kind of see this line at a lower and lower frequency. So each channel corresponds to a different cosmological distance, and therefore a different redshift. And this type of survey is generally less time consuming compared to a spectroscopic galaxy survey, which requires very high sensitivity to detect each individual galaxy. And so far, there have been two reported detection of H1 with intensity mapping experiment, and both of them were from the GBT telescope. And the first one was done with that also too in cross correlation with GBT map and deep to optical galaxy survey at redshift 0.8. And the second one was with Wiggle-Z dark energy survey cross correlation. And there has been no detection in the autocorrelation, and that is still yet to come. And in this slide, I'm going to give you an description, like what is the difference between a single dish intensity mapping and an interferometric intensity mapping. So the idea in a single dish intensity mapping experiment is to map a large area of the sky with the telescope beam. So each individual circles that you see here is the primary field of view of the antenna, and we sort of move the antenna across the sky so that we can have a large survey area from the sky. But in the single dish mode, we cannot really see inside each of these primary field of view. Uh, and the idea here is that we can probe large area of the sky, and from there we can estimate we can probe the large scale structure. And in comparison, like in the interferometer mode, we are restricted to like a single field of view. So the idea here is to point your telescope in the interferometry mode to various fields, say Cosmos, CDFS, XMMLSS, and study the structure inside the field of view. So in the interferometric mode, we can actually we have better resolution, so we can see the structure inside each field of view, and we can, in principle, get a deep pointing on each field to have the power spectrum estimation, or we can individually measure the power spectrum from different fields and then combine. In either way, we can have estimation of the power spectrum. And so there is a difference between the two, like in terms of which scale they probe. Like since the single dish mode, we have a large area of the sky, so we can really go small k values in the Fourier space. But in the interferometer mode, we are restricted by the smallest baseline that we have, and that gives us what is the smallest k mode we can probe within the interferometer mode. So from now on, I'm going to talk about the interferometry IM, not the single dish intensity mapping, and that's the talk is all about. So the first the thing that I'm going to talk about is that statistical measurement of the H1 with an interferometer. So here we are not talking about making images. Like images are always good. They are much more rich in information than a statistical detection. So the idea here is to first detect it in the statistical way, because in terms of sensitivity, that's we are going to get first. If there's a possibility of detection, and then we can have detection maybe in the imaging domain in the future. So the first try would be to detect it statistically, and that's where that becomes pretty interesting with interferometers. Like interferometers sort of gives us in the hybrid space that already is in the Fourier space that I'm going to explain now. So an interferometer is like a collection of many telescopes, and if you know a little bit about the interferometers, what is done is like the signal from each of the antennas are cross correlated, and each antenna pair is called the base element of an interferometer, which is also called the baseline. So each baseline actually measures the spatial correlation of electric field from the sky, which is actually called the visibility. And this visibility is recorded per baseline at individual frequency in the band that is being used. So in terms about the cosmology, that if you talk about this theta as the real space, we want to study the fluctuation in the real space, or the real space volume that is that K space is the Fourier domain. So the fluctuation in the theta space and the fluctuation in the K space they're Fourier pairs. And in the radio interferometry, the sky fluctuation that we see, they are in the recorded data is in the visibility domain. And this UV and eta is a Fourier pair of the frequency. they are Fourier pair of the real space coordinates theta x, theta y, and frequency. So intuitively, you can sort of understand that there is a one-to-one correspondence between the cosmological K space and the radio interferometry variables, say UV and eta. So if we can measure this visibility, we can actually calculate the cosmological power spectrum from the calculated visibility. And the one-to-one correspondence between the UV, the coordinates UV and eta, and the kx, ky, kz are shown in the right box. And the idea here is that like the power spectra, which is actually the autocorrelation of the fluctuation, with the same quantity we can actually get by correlating the visibilities. So the visibility square is one manifestation of the cosmological power spectra that we are that we want to detect. And so given an interferometer, there is an interesting question like, then what are the k-space that we're going to probe with an interferometer? So let's say if we have an interferometer where the antennas are very closely spaced, so you have like lots of short baselines. And there is another antenna configuration where the antennas are distributed far away, and you have the baselines are baselines are very large. So in the k space, the k perpendicular space is is on the plane of the sky. So this is proportional to the baseline length. So for this configuration, you can actually have the k modes that are accessible to this baseline configuration are shown in the blue shade, and the one on the green shows the baseline configuration of the k modes accessible by this configuration. So you can understand, like if we have a baseline configuration something like this, and the antennas are like far apart, the case values will be very high, and that may not be very cosmologically interesting, because as we go to higher and higher k, you are going into the much nonlinear region. Just to point it out, like the baseline configuration plays a big role, like which are the k modes that are accessible to us with that baseline configuration, and that plays a big role here. And since we are talking about the statistical measurement of the H1, so there are various ways to calculate the power spectrum from the interferometric measurements. The one that we have done here is in the simulation. The pipeline is called the delay power spectrum methodology. So it's a special variant among the visibility-based power spectrum estimators, where you directly Fourier transform the visibility that is measured per baseline along the frequency axis. And there is an like inherent advantage of such delay power spectrum, is that in the delay space, the spectrally smooth foregrounds are isolated in a wedge-shaped region, and that we'll see in later slides that how that makes our life easier in terms of foreground isolation. And this is actually, but there is one small caveat in this kind of approach, is that since we are taking a Fourier transform of per physical baseline, and each physical baseline, like in the frequency domain, probes various is a range of U values. So as you go like higher in the channel, your the U values for a given physical baseline, they change. So they probe various other different k perpendicular modes, and that is not that like, and this effect is much more severe if we go to higher baselines. So till the time we are restricted to short baselines and small frequency range, the delay power spectrum is a good approximation to the actual cosmological 3D H1 power spectrum. And this has been studied widely for epoch of reionization, like similar epoch of reionization experiments, something like Paper, NWA, HERA, etc. And if we, and the next step would be to explain like how from the visibility we are going to get the power spectrum. So as I said before, like there is a one-to-one correspondence between the UV and tau to the kx, ky, perpendicular coordinates. So each visibility measurement, if we start with each visibility measurement, take a Fourier transform along the frequency. So our data product are in the UV tau domain. And for each data point in this domain, we can actually calculate the power in the k domain. So the idea is that populate as many as points in this domain, and we sort of have a space filled with points in the k space, and we can easily calculate the power spectrum from just squaring the visibilities and multiplied by with other some normalization constants. That depends on the primary beam, what frequency we are seeing, things like that. And so if we just see a schematic of the interferometric pipeline, so the idea here is that with a radio interferometer like Meerkat, we are seeing a real space volume, say, which is at a distance, co-moving distance r from Earth, and we are seeing, say, a co-moving depth delta r, which depends on the what bandwidth we are using, and that gives us space in the k space filled with in the domain kx, ky, and k perpendicular. So kx and ky are on the plane of the sky, and k parallel is along the line of sight. And from such a cylindrical power spectrum domain, we can further calculate we're calling it 2D power spectrum or 1D power spectrum. So the idea here is that the average, take a circular average along the kx and ky to form a single k perp vector. So, and just show the power as a color plot in this 2D plot. Or we can do a circular or spherical averaging in like kx, ky, and k perp to make a single k vector. So we are going to show the 1D power spectrum as pk versus k. So we present both to show various features of the power spectrum and things like that. So that's the basic schematic of how we calculate power spectrum from interferometric observations. And so next, I'm going to talk about briefly about an introduction to the Meerkat radio telescope. So it's a well-known precursor to the SK, and it's located in the Karoo region in South Africa. So currently, it has 64 dish antennas. Each antenna has 13.5 meter diameter, and the central core of the antenna distribution that you see here as a central square, it has about 48 antennas, and the core region is about 1 kilometer. And there are some other 16 antennas which are distributed around like up to a radius of 4 kilometers from the center. And so this tells us that it has a dense core, and we got a lot of short baselines. So in the interferometric mode, the K modes that are accessible to us are well in the cosmological regime. We are not getting like very small K values as in like single dish measurements, but we'll be in the linear regime with such antenna distribution. And so the dense K, that's because of the dense core, we have higher sensitivity for the low K perpendicular modes. And it currently operates in the L band range, which is between 856 to 1712 megahertz. And this actually shows that what are the K modes that are accessible to us. So the rate curve here shows us the K modes that will be that are accessible to us in the single dish mode, and there is a separate project going on in parallel to the intensity mapping with the Meerkat single dish. And the one that we are currently working on is the interferometric mode. So these are the kind of scales that we are talking about that we can have access with the interferometric data. So the requirement here is that we need deep single pointing observation so that we have better sensitivity. And with that kind of data, we can integrate down to actually put constraint on the H-on power spectrum. And that's the goal here. So why do we need a simulation pipeline? So in the beginning, I said like we have built a simulation pipeline to demonstrate like what we can achieve. So the purpose of a simulation pipeline is to demonstrate that interferometric intensity mapping is a complementary to single dish interferometric experiments. So and the idea here is to emulate the actual Meerkat interferometric observation, and to check the possibility of statistical detection with the Meerkat on semi-linear scales. And if we have input to cosmological power spectrum in the simulation pipeline, can we actually recover it at the end? Like if we add the realistic system noise and the foregrounds, so can we actually detect our input H1 model power spectrum in presence of such contaminations? So therefore, we want to make a pipeline that can mimic an end-to-end data collection and analysis pipeline. That's the goal here. So that's why we're working on this, and we have made some sensitivity estimates with our simulation pipeline. And if you ask, like, why do we need data for simulation? Because the reason here is that the observed that visibility that is the primary data product of an interferometer is consists of like three parts. So there are the visibility have three components. There are like we get visibility from the actual cosmological signal. Let's call it VH1, and we have the contribution from the thermal noise, and also a contribution from the various foregrounds like extragalactic foregrounds and then diffuse synchrotron emission. So for the H1 thermal noise and foregrounds to simulate these things, we need the baseline distribution. And so we can get it from the actual data. We could simulate it from the antenna distribution, but we can also get it from the actual Meerkat observation as well. And we can actually then compare our outcome to the power spectrum that we obtain from the data. And we can also get the foreground visibilities that the model that we can also get from the continuum image that we can build from the actual calibrated data. So the continuum image that we can make will be fed as a foreground model in our simulation pipeline. That's why we need data for our simulation. And we have chosen the MIGHTEE survey. So for our project, we could use any deep single pointing observation, but we have chosen MIGHTEE because the data is already there. So we started with the MIGHTEE survey. So brief introduction about the MIGHTEE survey is that it's a Meerkat International Gigahertz Tiered Extragalactic Exploration. That's the full form. And the idea is to survey 4 well-known extragalactic fields, and like Cosmos CDFS and XMMLSS and ELISS1. And there will be total 20 square degrees of survey in the both continuum and the H1 mode. And these are the various science goals for the MIGHTEE project itself, like AGN evolution, star formation activity, and the evolution of the neutral hydrogen in the universe, and the properties of the cosmic magnetic fields, and various other things. So we are currently not working on those science goals. Our goal is to use the MIGHTEE observation to put constraint on the H1 power spectrum. And if you are interested about the MIGHTEE survey and you want to know more about it, please read the paper by Matt Jarvis, 2017. And the figure in the bottom here shows the various pointings that will be put for XMM, LSS, CDFS, and ELISS1 in the MIGHTEE mode. So these are shown in the yellow curve, and the other region in the box in the other colors are the survey that are done for some other multi-wavelength survey, so that we can cross-match results between MIGHTEE and other surveys. And the pointings for Cosmos are not shown here because they will be done mostly on single pointing, and maybe some pointings will differ a little bit, but they'll be mostly done, that will be a single pointing observation. So for our work, we have taken the data from the Cosmos observation that I'll come later. So in this plot, I show you the 4 fields accessed by the MIGHTEE survey. And you can see that all the 4 fields are like quite away from the galactic disk, where the diffuse synchrotron emission is maximum. So we can have like very low contamination from the galactic synchrotron emission. And that's a good thing for us, so that we don't need to worry much about this contamination. But we'll still need to have an estimate for the diffuse component of the foreground, how much it contaminates our power spectrum. So the data that we use are from this Cosmos field. And the data is about, say, 11.2 hours of duration on source integration, and it's spanned over 2 nights in the frequency band 950 to 1150 megahertz. So it actually covers the full L band. So, but the data that we have selected is just sub-band data, so that we can actually make images faster and put some results. And the primary flux bandpass calibration and flagging was done with this IDEA process Meerkat pipeline, and which is a purpose-built pipeline to calibrate Meerkat interferometric data, which uses CASA-based routines for flux calibration and flagging. And after this post calibration by this process Meerkat, we actually do the self calibration and the deconvolutions ourselves with CASA, and so using gain cal and tclil, things like that. If you are that's a bit technical. And we also in the continuum mode, we have actually the flux and also the spectral variation along the frequency, so that we can put both in our foreground model. And this is the image on the right that we have produced from this integration of the 11.2 hours of data in the 950 to 1150 megahertz band. And we are able to get an RMS about 10 microjansky per beam in the image. And if you look carefully in the image, that you see that the discrete extragalactic sources dominate in this image. We see very little or no diffuse galactic synchronous emission. So it just tells us that it has a weak contribution in the total foreground budget. But we expect to see it after we subtract fully the point sources, and then probably we can see the diffuse galactic component. So therefore, as the first iteration in our foreground model, we are only considering the contribution from the point sources, the bright point sources. At the moment, we are not putting the contribution from the galactic synchronous emission in our total foreground model. And in the foreground model, we have total, say, about 3,391 extragalactic sources, mostly all in Miljansky flux range. And so this is what we use as our foreground model in the simulation pipeline. And here I explain you what is exactly our power spectrum pipeline is like. So we have our visibilities. So we can actually simulate the visibilities, or we can take the actual calibrated visibilities. And from there, we can estimate the power spectrum. So we start with the visibility per baseline. So this can be either from simulation or from the actual data. And for our simulation, we take the foreground visibility as from the continuum model. And per baseline, we also generate the thermal noise. And we take it as a Gaussian random process, which we populate the real and imaginary part of the visibility for the thermal noise component with this sigma. And for the power spectrum computation, we do not take the full 950 to 1150 megahertz. We'd rather take a much smaller band. So this is about, say, 46 megahertz band, centered about, say, 1.12 gigahertz. So that corresponds to roughly, say, let's say 0.27. So the first thing we do for our work, that we grid the visibilities on the UV plane. That has cell size is about delta U, delta V is about 60 lambda. So this choice of this cell size is motivated by the primary beam. So that the size of the primary beam tells us like how much our cell size should be in the UV grid. And then within the UV, within every cell, then we average the visibilities, and then we delay transform along the frequency with an FFT and applied by a spectral weighting function. That is called the Blackman-Harris window. That's the Blackman-Harris window that we use here. So the purpose of using a spectral weighting function is to minimize the contamination from the foreground region to the cleaner K-space region. Because if we don't apply a window, there will be a sharp cut along the edge of the band, and that will leak power from foreground wedge to the higher K parallel modes. So that's the reason we use the window. And after we have calculated the 3D power spectrum, and then we can calculate the both 2D and 1D power spectrum with inverse various weighting. So that's the steps that we use in the power spectrum pipeline that I have just explained briefly here. And this plot shows the population or the density of the UV points on the UV grid So this is done after grading grading the visibilities. So what you see here is actually the color represents the number of UV points within each cell. And so you can see that we have more baselines at the center, and the baseline density or baseline distribution that sort of falls off as we go to higher UV values. And the plot on the right shows the same plot, but as in a 1D way. So in the x-axis, we plot the UV distance from the center, and then the number of UV points are shown as in the y-axis. So you see that we have higher population or higher density of UV points at small UV distance, and then it sort of falls off at higher UV values. So this actually tells us that we have higher sensitivity. So on the top x-axis, what we show here is the K perpendicular modes that are accessed by these baselines. So we have higher sensitivity at the low K perp, and it sort of falls off at high K perp values. And the first result that I show from the power pipeline is that in the first step, we want to check if we have a model input H1 power spectrum, can we actually recover it without any contamination from system noise or foreground? So in our simulation pipeline, we first started with an input model power spectrum. We generated the visibilities, and we just ran through our pipeline and tried to see that can we actually recover the H1 power spectrum. So this is our input H1 model power spectrum, and this is a single realization of after we got our results from pipeline. This is a 2D plot in the K perp, K parallel space, and this is a 1D plot. This blue plus points are the expected H1, and the various curves are from various realization of our simulation pipeline. So this is for only H1 only simulations. So this actually tells us that our simulation works well, that we can actually recover the H1 power spectrum without any contamination from system noise or foregrounds. The next step would be to add the system noise and foregrounds that we're going to see later. So before I talk about adding foregrounds into a simulation, so I want to talk about like how we deal with the foreground in a power spectrum. So this is actually, we do not try to subtract the foregrounds here. Rather, we try to follow an approach. It's called the foreground isolation approach. So the idea here is that the H1 that we're trying to see or trying to detect, it has a symmetric nature in the Fourier space, because the fluctuations have no specific direction. They are isotropic. So in the Fourier space, the fluctuation in the K space are also expected to be isotropic. So there is no preferred direction for H1. But on the other hand, foregrounds, they have a smooth spectra. So, and if we, and in the Fourier domain, if we take a smooth function, they are restricted to like few small Fourier modes, and the higher Fourier modes are effectively can be expected to be foreground free. So on the right side, you can see that in the Fourier domain, the contribution from the foreground are restricted to like a few K parallel modes, and the higher K parallel modes are relatively free from any foreground contamination. And we can use this H1 and foreground, you can use this property to distinguish foreground from H1. So therefore, in this plot, I show you the results from our simulation pipeline. So the first is when we just include the H1 contribution that I have already shown earlier. And the second plot here is that when we add the thermal noise component. So if you look at this plot, we see that we have low thermal noise, and it sort of increases as you go to high K perp values. And it actually follows the baseline distribution. As I said earlier, we have more baselines at small K perp values. That's why the sensitivity is higher at low K perp values, and it sort of increases as you go high and high K perp modes. And when we add the foregrounds, we see that the foregrounds are well isolated to few K parallel modes. So we see this sort of this foreground wedge here. The reason we see a wedge is because this K parallel is proportional to the actual delay in the antenna, the two antennas in a given baseline. So So if we go high and high K per values, they are actually probing longer baselines, and the delay that ranges from like 0 to 0 that comes from the zenith, and the maximum when the source is at the horizon. So if we have a longer baseline, we have longer delay, so this span is higher. So that's why the foreground region takes this wedge shaped form here. So the idea here is that since we are taking the foreground isolation approach, is to cut out this region completely. So we do not take these pixels into consideration for any Paul spectrum estimation. We just take the region beyond the foreground wedge for estimating the H1. So this region is relatively free from any point source foreground contamination, and that's a good thing. So now next we want to compare like the simulation from the actual data. Like we also have the access to the real data that we used for the imaging to make the foreground model. So you had used the same calibrated data and ran through the same pipeline to make the Paul spectrum. This is what we see. So the plot on the left is already shown on the last slide. So this is from our full simulation, and the plot on the right is from the actual calibrated data that we use for our imaging. So this is from the 11.2 hours MIGHTEE field, Cosmos field. And if we compare these two plots, we actually see a very good agreement between the two. There are a few systematics in the real data that we still need to look carefully. But in terms of the noise feature, the sensitivity, they are in good agreement. So that tells us that we are on the right track, and our simulation pipeline is doing what it is supposed to do. And then next we compared the result that the noise Paul spectrum with the Stokes V visibilities. We can also calculate the Stokes V visibilities from our calibrated data set, and Stokes V visibilities are supposed to be if there are no polarized foregrounds, they're supposed to mimic the noise Paul spectrum. So they are supposed to actually give the noise values. So what we tried to do here is take a ratio between the Stokes V Paul spectrum and then our thermal noise Paul spectrum, and we took a ratio between the two, and we see that there is a good match between the two. Most of the points lie around 1, but there is a region here at the shown in the black box here. So this is probably because of the polarization leakage, which is expected at these K values. So that's why there is excess power in the Stokes V, which is believed to be polarization leakage, but we still have to look carefully there. But otherwise, if we look at the regions away from this box, there is a good agreement between the Stokes V and the thermal noise simulation. So we have our model of thermal noise is actually correct. And in this plot, I show the 1D Paul spectrum that we have calculated from the actual from a simulation. And this is shown at the red points. So what we have done here is that we have run our simulation 1,000 realization, we have generated 1,000 realization of our simulation pipeline for the 11.2 hours case, and all those 1D Paul spectrum are shown in this plot. And we have excluded the foreground wedge to calculate the 1D Paul spectrum, and each marker shows the average of all 1,000 realizations. And the dashed curve show the average noise Paul spectrum. So when we have only thermal noise as input in our simulation pipeline. So this is the average thermal noise Paul spectrum. This is also calculated from averaged over 1,000 realizations. And apart from that, we have also considered like 3 hypothetical cases where we have, say, 2 times of the data that we already have, so 2 times 11.2, 5 times, and 10 times. So we just want to check like how deep we can go if we had more data, and what kind of constraint that we can achieve. And so the way we have done here is that we have taken the same baseline distribution, and we just assume repeated measurement on those baselines. So we are not gaining any extra baseline information there. It's just on the same baseline, we are adding visibilities. And you can see an improvement in the sensitivity as we go, like if we go deep and deep with the integration hours. And the next plot that I show here is that from 1000 relation in the earlier plot, we have subtracted the average thermal noise power spectrum that was shown in the red that was shown in as a dashed curve, and as a distribution of that those like the first 4 K modes like 1, 2, 3, 4 as the histograms. And you can see that with the increasing duration of hours, the distribution is Gaussian, but the width decreases. That gives us we can get tighter and tighter constraint on the H1 power spectrum with increasing duration of observation. And that is shown here as in the last plot here. So the first 4 points, and these are the 1 sigma error bars that we get from the 3 cases, say 11.2 point times 2, 5, and 10. So what it shows is a promising thing that within the existing MIGHTEE survey, we can actually obtain the constraint on the H1 power spectrum, and we can actually have a detection with such data duration. And so far, these hypothetical cases are for deep integration on single pointing. In principle, we can also combine, say, power spectrum for other fields. So the one here is only is shown only for the Cosmos field, but we'll also have data from other fields as well. So what you can do is that we can calculate the power spectrum from those fields individually and then combine, and that can also reduce the uncertainty. So that's a promising thing that we can actually have the detection with the MIGHTEE survey, and that's the point. That's the thing that we wanted to show. So that's the final slide of this talk, and I'll just conclude with this slide that intensity mapping is a very powerful probe and is capable of providing useful cosmological constraints. And interferometric intensity mapping can provide complementary probe as to single-disk intensity mapping. But single-disk intensity mapping they are supposed to go to much deeper in the K space. But with interferometer, we are sort of constrained in the semi-linear scales. And Meerkat with the MIGHTEE survey is capable to provide constraint on the H1 power spectrum. And we have built a visibility-based power simulation pipeline, and we have provided sensitivity estimates that we can obtain with the current MIGHTEE data. And in future, we'll also include many other complications, real life complications with the pipeline, such as the Meerkat primary beam and how it changes in the frequency domain, and many other things such as non-coplanarity of the baseline and how that contaminates the actual signal, H1 signal. And our final goal will be to build a robust end-to-end pipeline to detect H1 with Meerkat interferometer. So now I'll stop, and thank you.
Yes, thanks a lot for this very insightful talk. I hope everyone enjoyed it. I'll quickly conclude the live stream on YouTube. I hope people there watching also found it very useful. And if you want to ask questions, you can put them in the comment section as usual, and see you next semester.